In this video, we're going to look at the different ways we can create magnetic fields, and these are called electromagnets. So what an electromagnet is you have a moving electric field. Okay, so, well, I should say a moving electric field, or aka moving charge. Current means moving charge. So if you have a moving charge, you have a magnetic field because you have a moving electric field. Okay, just a quick info. So if the first case here is a straight wire, like you just connect a wire, you send current through it. Actually, got magnetic field leh. How do we know how the magnetic field looks like? You need to use your right hand. So you stick out your right hand, you hold a pen, and then you kind of see where your fingers curl. So like this person, the fingers curl this way, and that is the direction of the magnetic field, all circles around it. So if you take the top view of this thing, and let me draw a square. Okay, this is the paper. What we will see is a current coming out of the page. So when you have a current coming out of the page, usually we put a dot. 3D like coming out. We cannot draw it's coming out. Your eye is looking from on top here. This is your eye, top view. Okay, so usually in physics we put a dot like this, or dot in a circle. That is out of the page. And if the current or field or whatever is going into the page, we put an X. And this means into page. Okay, just a quick note. So how are we going to draw the field lines? Okay lah. So very close to the wire, you're going to have very strong field lines. As you get further and further away, they become more spread out. I try to draw a few lah. Okay, here got some more. Okay. So all these are going anti-clockwise around the wire. So we're going to draw them like this. How to check? You take your finger and you put it in a way where your thumb is coming out of the screen. Slam your thumb on the screen right now and see whether your fingers curl in the direction that I just draw. Okay, put your hand on the screen. Alright, so that is the top view of it. And if we look at the front view, so top view just now, that one, front view will be something like, maybe you look from this side. That kind of makes sense. Okay, so your wire will be like this. You have your paper, which is kind of pretty thin. I guess I should draw something thicker a little bit. Paper. So this is your paper. This is your wire. Where is current flowing? Up. So that you can imagine all the tiny charges inside this wire are moving. And moving charges generate magnetic field. So if you want to draw the magnetic B field now, you have to say, Miss, how to draw this one? Is looking from the side. Can. You draw like this. On the right side, it is going into the paper. On the left side, it's coming out of the paper. So you put X. Wrong side. Right hand coming out. Coming out. Wrong direction. If your thumb is up, or your fingers should be pointing at you. So this is out of page. Come out, and then to the right, it will go in. So this is all into the page. Okay, this is if your current is moving up. What if you turn your current upside down? How would it be different? Well, you could just do this, rub off the current, and say, oh, what if now I change the direction of current? I send it down. Then your magnetic field will be a bit different. Give your bad thumbs down sign, and you see how your fingers curl. So on the left side, your fingers are going into the page. So you draw X's. So this is into the page, or into the screen lah. Okay, into the screen. And then your thumb will curl out on the right side, and that is coming out of the screen, or out of the page. So out of page. Okay, so know how to use your thumb in top, side, bottom, left, right, different kind of thing. So there is an equation to calculate the magnetic field at any point around this wire. Usually it will be given to you during exams, but this is how it looks like. The magnetic flux density, or field strength, is mu naught I over 2 pi r. Do we need to know how this came to be? No, you don't need to know that. Maybe if you study physics or some kind of electricity thing in the future, you might have to derive this. But for now, we don't care about it. So I is what? I is a current. R here is the distance from wire. How far away in terms of a radius are you? So distance from wire. So let's say I want to measure the electric field strength here. Then I have to draw a radius R lor. R. Okay, that's how you can do that. What is mu naught? This is a new constant that we haven't exactly used before. So this is what we call the permeability of free space. This constant basically is just saying what type of material your wire is in lah. Okay, so is this in air? These are all air ma. Air. Okay lah, then we consider it like air. But there is a constant, so this constant value is 4 pi times 10 to the negative 7. You can check this in your question paper. There's a formula sheet. That's where you can see what the value is. So look at all these electric fields. This is the first one. Let's look at another way to generate magnetic fields. That will be up here. Okay, so you have one wire. What if you have two wires left? Then how? You still have to use your right hand, but now on one side, you have to put your thumbs up like this. On the other side, you have to put your thumbs down like this. Well, how to draw? Thumbs up, thumbs down. You put your hand like that lah, okay? Then you will see this particular pattern swirling around like this. Okay, so it's another way to do this. A note is, if you see in past year, this conductor will be a wire, right? And it can be many turns of wire lah. So it can be n number of turns. What is n number of turns? I go like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Many turns. So that will be creating a stronger magnetic field. Okay, but that's what it means by n turns. So if you look at the side view of this setup, we can try draw on the side. If you look from the side, you will see firstly this coil that is like this. Don't know how many turns. Okay, current can go up here, current can go down there. Now, how will the magnetic field look like if you look at the side view? You have to kind of imagine a little bit. On the left of this wire, okay, here remember your thumb. On the left, it is coming thumb out of the page. So here you put a dot. Then in the middle is going in. You curl your thumb around it. Okay, hold a coil and curl your thumb to see where it's going. And on the other side, you are putting thumbs down. So go into the page and out of the page over here. So do your thumbs exercise. It'll be quite helpful for you to learn how to visualize the magnetic field when you're solving questions later. Now the top view will look something like this if we are looking at the paper from the top. This is our paper. You have your wire going out of the page here, and the other one is going into the page. How to see? Out, in, out of paper, into paper. So you have to draw the loops kind of similar like this. So it looks gonna look like that. Okay, out of the page means curling this way. Use your thumb. In the middle, it's very interesting. It might be a straight line like this going up. Okay, then the rest you just kind of shape it around like that. So it's helpful to practice drawing into the page, curl around like this. Pew, pew. Okay, so that is how you can visualize magnetic fields if you have a loop like this. How many turns there are. There is an equation for it. They usually, again, will give it to you. But FYI, here's how the equation look like. The magnetic field strength and the middle right here, X marks the spot. That can be calculated by mu naught, number of turns, the current through the whole coil, should be the same lah, left side and right side, divided by 2 times the radius. This radius here refers to the radius of your coil now. So I'll just put here radius of coil. This one current lah. Current. And N is number of turns of the coil. So this is one way you will see people do experiments to generate electric field in all kinds of fields of study. Okay? One quick thing to note is how you can use your thumb and your hand, your right hand, in a slightly different way. Now, if you notice, here, the thumb up here refers to B field, and your fingers, the curl of your fingers can be current. You're like, Miss, isn't that the other way from the other right hand grip rule? Yeah. The other right hand grip rule, the thumb is the current and the fingers show the curl of the B field. But you can also use it in another way where your thumb is the B field and your fingers show the curl of the current. Also can. How can you apply that here? Well, if you look at the top view, this one here, right? So the middle line is where the magnetic field will point. So maybe I will say, what if I align my thumb right there, like literally there, and my thumb is the B field, which is pointing up. And the fingers will then curl out of the page on the left and into the page on the right, which is exactly what we just drew right here. So there's a few ways you can do this, you know. What do you want your thumb to be? B and I. It depends lah. Your fingers are I, then your thumb is B lor. If your thumb is I, then your fingers are B lor. We can use it both ways. So that leads us to the next magnet actually, called the solenoid. Now how this solenoid is created is kind of simple. You have something like a material, could be a metal stick, could be a toilet paper roll. You see my eye right there? And you just grab a wire and then you start coiling it around this thing, of course in a nicer fashion lah. Alright, so when you run a current through this coil, it's what we call a solenoid. So you just need to follow which direction the current is going and figure out how the magnetic field would look like. Okay, so if we look at this diagram, they drawn a very nice one for us, not just my toilet paper. But here, it is wound in such a way and current is sent in through the right side. So here is in, current out. So which one you want to use? Your thumb is current or your thumb is magnetic field? In this case, if you want to use current as your thumb, it's very hard because then your thumb have to keep turning. Your thumb turn in, turn out, turn in, turn out. Can lah, but your thumb will be moving a lot. So it's easier to just say, okay, we are going to use our thumb as the direction of the field, which is B. And how do we know it's pointing in direction? That's because we look at how the current is coiling around. And we align our fingers such that it is coiling around with the current like that. Okay, so your fingers now is the current. Follows the curling direction of the current. And the B field will be pointing where your thumb is pointing. Go try hold something in your hand now, okay? Now if you look on the right, this shows what's actually happening inside this object. Okay, the magnetic field inside there. So it's a little bit different, the current now. So you can see the currents coming in, coil like that, like that, like that, like that, like that. So kind of think of how if you place your hand on that thing, it'll be something like this. I don't know the camera is flipped or not, but you try to place your hand, okay? Place in the hand such that your fingers are the direction of all those tiny little current arrows that I just draw. Notice something interesting inside the field. You see, the field inside looks pretty uniform. The lines are equally spaced, and that is something interesting. You can kind of make a uniform magnetic field inside a solenoid. That's what makes this one special. The rest that we look at just now, they are a bit like a circular magnetic field. This one also kind of circular, curve here, curve there, but this one is a bit special because uniform magnetic field. Very good. We can do experiments now. So that is one thing to note. If we draw a graph of B against L, it will look something like this. So middle part is roughly uniform until where? Somewhere until here maybe. So this part looks pretty uniform. Other than that, if you go any further, you notice that the gray color field lines are getting further and further apart. Means the field is weaker already outside here. Whereas inside there is uniform and quite strong. So if you want to plot a graph, maybe around here I'll give it a nice flat peak and then the field will decrease until you're outside the field is just like quite low already. So same for this side, feel pretty strong and then decreases as you go to the edge of this solenoid. So up here is almost a straight line kind of thing, almost. But this is what we call the magnetic field strength of the uniform part of the solenoid. So pretty strong. We like assume it's kind of straight lah. There's the equation for that. We'll look at it in a bit. But oh, one more thing. Top view. Got so excited I forgot about it. So you look at the top view. It's pretty much the same thing of the solenoid. It's just down, and then you see like lines and lines and lines. Oh, you won't see this part. You see like lines. So nothing too interesting here. Maybe here it's coming out of the page. Then here it's going into the page. Sure. Yeah. Not too much over there. So remember I mentioned the uniform field inside the solenoid? It's kind of uniform near the center. If you have a really long solenoid, then maybe the flat part is a bit bigger lah. Okay, so this part is the where it's kind of uniform. Kind of. So there is an equation to calculate the magnetic field strength. I should say flux density. That is mu naught Ni over L. What is N? N is the number of coil. So this N. How to count now? Something like this law. 1 loop, 2 loop, 3 loop, 4, 5, 6, 7, 8, 9, 10. Something like that. Rough estimate. How many loops you can count. Okay. And L there is the length of the solenoid. How big is your coil exactly? Okay. And from there you can calculate the B, which is the uniform one somewhere in the middle, which is the approximately constant for the middle part. Somewhere here. Okay, beyond that it starts to change a little bit. The final one is a variation of this. So people discovered that, we can make uniform fields with solenoids. But if I want to do an experiment, I want to stick something into the solenoid field. I want to put a probe inside there. I can't exactly do it if it's, a bunch of coils. So what they did is, people come up with the Helmholtz coil. This one. It's like solenoid but got a hole in the middle here. You see this hole here? So you have coils on this end, coils on the other end, and in between you can do experiments. You can put stuff in there, you can put electrons, you can pretty much do a lot of stuff. So how is this different? Not much different actually. It's pretty much the same as the solenoid, except that now you have holes. So if I were to draw out the Helmholtz coil top view, it looks something like this. So that is, I guess you could call coil number 1. Here, coil number 2. So this is number 1, number 2. Kind of like that lah, just so you know, can orient your brain a bit. So what is the current flowing in the coil? Let's see. You see the battery down here? Current. Oh, they draw arrow for us. So ammeter flowing this way. So here it's coming up, loop down, and then up, and then down, and then up, and then down, and up. So for coil 1, on the top part, the current is coming out of the page. So I'm going to put a dot there. And on the other end, it's going down. So I put the X. You kind of imagine looking from the top down. Your eye is on top like that, looking down on the coil. Same thing for number 2. Let's check the current flow. Where is it flowing? So the orange arrow I'm drawing here, current flow. Here is going up, loop down, up. Use your eyes to follow the trail down, up and down. So same thing also, up. So it is coming out of the screen or out of the page, and going down, which is into the page or screen. Imagine this way, okay? So imagine you're looking at the top-down thing. If you want to draw a loop, sure, it'll look like that. Zoom, zoom, zoom. Go down here, go up, loop, and loop, and loop. Okay, that's how you can follow the trail. Now the magnetic field, okay. So they kind of draw a very nice magnetic field already. The middle one, which hand should you use? Right hand rule. Which one you want to use for your feel or thumb? In this case, it's probably easier to use your thumb as magnetic field. So here I'm going to say thumb is going to be the B. Fingers, let's do the current. Fingers. So you see the current is going to, come out from this side and loop over here. So you kind of lie your hand down, and you will find that your thumb will point in this direction. So that will be the magnetic field. But actually, also, if you use your thumb as the current, you will notice that, means here go inside, it should loop like that also. Correct lah, okay? So you also have loops like that. If you stick your thumb into the computer screen right now, what do you get? Oh, stick your thumb out of the computer screen, you will get that small circular loop. For down there at the X, if you stick your thumb into the computer screen, you will get loops in this direction also. So they didn't draw in the picture, right? Yeah lah, they didn't draw. Show the whole thing. Okay. Everything in between, almost there. It will be look something like this. You know, the lines can't touch, so it's like, not exactly uniform, but it's trying really hard to be so. So this is how it will look like lah. The feel kind of a little bit kinky and curvy here and there. But that's approximately uniform in the middle if you stick right in the highlighted section right there. Okay, so this is one of the tools which you will use in experiments, in machines. The Helmholtz coils got a space in the middle so that you can put stuff inside there. You see this loop here? Okay, solenoid, very nice uniform feel, but you cannot stick stuff inside there so easily. Okay, so that's all the types of magnets you need to know here. Do you need to draw this for exam? No, you don't need to draw the magnetic field for exam, but they may tell you, oh, we have a solenoid like this. Calculate the field or show which direction the field is pointing to. So you kind of need to know how the field would look like, which is this one on the right. Okay, or things like this. Calculate the magnetic flux density at a certain radius from the wire. You need to know, oh, if it's wire, the field curl around like that. So what I suggest is practice using your right hand thumb. Go and try all these things, and if I do not make sense to you, go and look at your notes again and use your hand on the paper and you try to see how to turn your hand so that it makes sense to you. Okay, so that's all for this first part, electromagnets and how you can calculate and know how the magnetic field looks like. Okay, that's all for this section. See you in the next one.